Hi there. As you can see on the screen behind me, today's topic is Hess's Law. Now, Hess's Law is something that's going to allow us to calculate energy and enthalpy changes for reactions that we can't actually do physically, that we can't actually perform. We're going to use reactions as if they were algebraic equations. So in the same way that you can solve a system of equations by manipulating the x and y and so on, we're going to do that with our reactants and products. That will require us to hold on, or that will require the law of conservation of energy to hold. In other words, energy can't be created or destroyed, it can only change forms. So if I take a look at this reaction here, where I have now the molar enthalpy of combustion of hydrogen, so hydrogen reacting with oxygen, where I'm forming 1 mole of water, that releases negative energy change, so it releases 242 kilojoules of energy. If I were to double the amount of reactants, I would also double the amount of products, and I would double the energy. So the energy change now is twice as large as it was before. If I took water and I converted it into a mole of hydrogen and half a mole of oxygen, if I did the reaction in the reverse direction, I would expect, law of conservation of energy, I would expect it now to be endothermic. I would require the same amount of energy, 242 kilojoules of energy. So we're going to make use of those principles in Hess's Law. Now, why would we do that? Well, as I mentioned before, it's going to allow us to calculate values for reactions that might not be physically possible, or ones that are physically difficult to actually perform. So we'll now calculate our energies. So here's a reaction system where it diagrammatically shows how Hess's Law works or why we use it. Now that's a little bit too much to take in all at once, so let's break it down. If I have the reaction solid sodium hydroxide reacting with hydrochloric acid, HCl, if I were to take the solid form and the solution and mix them together, I would have about 99 kilojoules of energy released, going from the reactants to the products, the top to the bottom. But I could also, let's take that reaction and the energy that I get. But if I look at it in steps, if I first take that sodium hydroxide and dissolve it in water, so now I make a sodium hydroxide solution, I will release a certain amount of energy. In this case, it's about 42 kilojoules, so negative 42 kilojoules of energy. If I then bring the hydrochloric acid, the HCl solution, I mix the two solutions, and I put that together, now I will have more energy released to the tune of about 57 kilojoules of energy. If I look at the two steps combined, and I compare that with the original of going just from the solid mixing with the solution to form my products, I get the same amount of energy, whether I do it in 2 steps or whether I do it in 1 step. So that's an illustration of how we use Hess's Law. I can take a reaction and do it stepwise. Now, if you've been in biology, the Krebs cycle would be an example of that, where I'm taking that glucose molecule through many steps, releasing energy at this step, at this step, at this step, and by the time I'm done, I've got all my energy collected, slightly slower fashion. Now, if we're doing a Hess's Law question, the question is going to look something like this. So we're not talking biology anymore, we're talking what it's going to look like in chemistry. So please write this question down, and then there'll be a few reactions afterwards. What we'll be doing is trying to calculate the energy change for this reaction, or a reaction that's given, and it's going to be based on certain other reactions that are given and the enthalpies are known. So we'll have reaction 1 and reaction 2 and reaction 3, and then pause the video at this point and write those down. Okay, so how are we going to use those? So we have those reactions, we have our target reaction, and we have our reactions to use. Now, I like to do it this way. So within my target reaction, I'll pick one of the, in this case, I picked the reactant. I'm going to try and find 4 moles of carbon solid from my given reactions, and I'm going to put it on the reactant side. And if I look at what I'm given, reaction number 2 had it as a reactant. It just didn't have enough. So I take reaction number 2 and I multiply it by 4. I multiply everything in reaction 2 by 4, and what I end up with is multiplying also the energy by 4. That gives me the 4 moles of carbon in the reactant side where I need it. But it also, as in doing that, it generates, let's call it a slight problem. I now have 4 moles of carbon dioxide on the products, and I don't want that. So my next step, and there's other ways of doing this, but my next step is to look at my reactions and find 4 moles of carbon dioxide as a reactant. So logically, this reaction produced 4 moles of carbon dioxide. I want to now use 4 moles of carbon dioxide as a reactant. So I look through and I find out that reaction number 1 has carbon dioxide as a product. So I reverse it. Now I write that by saying -1. I multiply it by the -1, and that just means reverse it. Not only do I reverse the entire reaction, so on paper the products became reactants, the reactants became products, but also my enthalpy will now flip signs. Now I do it this way, where I just put out on the side what I'm doing to the reaction. I'll do the same thing to the heat term. Now I've fixed my problem with carbon dioxide, but I also have put the C4H10 in the products where I needed it to be. I also, though, have generated, let's say, a new issue in that I've got water on the reactants, and I don't want water on the reactants. So now I'm looking to get rid of water. So water is a reactant. If I can produce it somewhere, get it on the product side, it will cancel out. Well, that's my last reaction. And this one, I had to multiply by 2.5. And multiplying it by 2.5, reaction number 3, multiplying everything by 2.5, that will make sure that I will have the right number of water molecules on the product side. I also then, of course, have to multiply the heat term by 2.5. Now at this point, what I can start to do is take the 2 reactants that I need. Okay, so I've got the 4 moles of carbon, I've got the 5 moles of hydrogen, and I've got the butane, the C4H10. I've got them all in the right state and the right side. I can now start to eliminate the things that show up on the reactant side and the product side. So my, where am I here? My 4 moles of carbon dioxide cancel out. My water that I don't want, I've got 5 on the reactants, 5 on the products, they cancel out. And I also have, all combined, I've got those oxygen molecules. I've got some on the reactant side, I've got some on the product side, and if I start to look and add up the different pieces, I find that they will also cancel out. Finally, and this is really why we were doing this in the first place, I take my energy terms. And I know that my net reaction is going to work, but now I add up all the energy terms, doing mathematically to the energy what I did to the reactions. So if one was multiplied by 4, the energy is multiplied by 4. If one was changed its direction, changed the sign, the energy term, same thing. Okay, there's a couple of things to help you with this, because Hess's law can get kind of messy, and all you have to really do is make sure you're being very, very systematic. Number one thing is for crossing them out. You can only cross them out if they are in exactly the same state and on opposite sides. So you cannot take an aqueous and cancel it with a solid. So if you think back to that sodium hydroxide one from earlier, where in one case it was sodium hydroxide solid, and one of the steps later was sodium hydroxide aqueous, you could not cancel those two out. The formula has to be exactly the same. You can't change it by a letter, not even the smallest atom. Have to be exactly the same thing. And finally, one has to be on the product side, one has to be on the reactant side. So as a net, if you have them on both sides the same amount, they cancel out, they don't count. And my suggestion for you is to be systematic. I started by finding a reactant and putting it in the right amount, in the right spot, but I could have started with a product. If you see, well, in the previous one, oxygen. Well, there's oxygen in all 3 reactions, so don't use it, or don't try and sort it out. Let it sort itself out at the end. If you have water showing up in multiple places, leave it to the end. For things that should cancel out, you should only have a couple of reactions that have it. One where it generates the problem, the other where it fixes the problem. I'm going to ask you to pause the video again and write these ones down, and I'm going to ask you to try it on your own. We'll come back in a moment and take it up. Okay, so you should have paused. You should have done this on your own, but let's have a look. Here's our target reaction. I'm going to start by generating a plan. I'm going to first get my product this time. No, I'm not. I'm going for my reactant again. I thought I was going to do the product. I'm going for my reactant. You may have gone for the product, and by the time you're done, we should have done the same things to the same reactions, and we should have the same answer. But put my boron solid where it needs to be. Find a problem. Okay, there's my problem. Try and solve the problem. Find a reaction that will allow me to eliminate that. Well, that requires reaction number 1 to be reversed. You might have done that first. You might have reversed reaction number 1 as your first step, and that's okay. The order doesn't matter. And then that will solve one problem, so we'll cancel that out. It also, happy accident, puts a product where I need it to be. Not only that, it generates a problem. Now I'm going to focus on the oxygen, and I'm going to fix that. Where am I here? I thought I was going to fix that. Oh, I've got a water problem too. By the time I'm done, I have to do something with the last reaction, reaction number 3. That will do a couple things. It will solve a problem that I had with water, cancel that out. It will finish solving a problem with the oxygen. So you'll notice I had some oxygen from reaction number 2, some oxygen from reaction number 1, and now the rest of the oxygen in reaction number 3. So I kind of left that to the end. And the final thing it's going to do is it's going to put my other reactant where I need it to be. So I'm being systematic. Trust the reactions, trust the math that you're doing. Finally, I'm going to figure out and confirm that indeed my target reaction has been met by working my plan, and most importantly, calculate the enthalpy for that, adding up the heat terms. If one ends up being minus, then I guess I could be subtracting it, right? But I'm going to add them exactly as they are. So maybe I'm adding negatives, maybe I'm adding positives, and doing all that great integer work. Okay, a lot to take in. It's actually not a difficult thing at all, as long as we're being systematic, as long as we're paying really close attention to the states, and whatever you do to the whatever you do to the reaction to put it where you need it to be, do exactly the same thing to the heat term, the enthalpy term, and it should actually work out and everything should fall into place. We'll try it out in class and talk to you then.